But it stops.
Okay. Got it. Okay, cool. So I want to talk about the progress in topological materials before I dive into my work to kind of help motivate what I'm doing. There's been, immense amount of progress in this field over the years, over the last few decades. I like this timeline that I pulled from this paper down in the corner here. I think it summarizes a lot of important developments that happened in this pretty short window from 2005 to 2016. You see some important theoretical developments in there, as well as experimental confirmations of things. But one thing I want to point out about this time period here between 2005 to 2016 is that there were only sort of a handful of predicted materials that had non-trivial band topology. It was a relatively small number. Most of the main ones are actually shown on this timeline, or their families are shown on this timeline. It wasn't until a year later, if we extend this timeline out a little bit, there we go, that we see sort of an explosion in the number of predicted topological materials. And this happens because we see this sort of mind-boggling high throughput searches that occur for topological materials. This is where a few research groups essentially did calculations for every material in various databases. So for example, the ICSD database, and then used very efficient tools like symmetry indicators or elementary band representations to say something about the presence or absence of non-trivial band topology in the ground state of these systems. So in the most recent iteration of this search, just published last year here in Science, actually this group said that about 88% of materials in the ICSD database support non-trivial topology of some type or another. Now this sounds really amazing and impressive, and it is, but there's sort of an open question here, or challenge, that was really, I think, nicely posed in a talk that I attended last year, given by Leslie Shoup, where, and she's kind of a collaborator of these groups, where she said, this is, amazing. We have all of these materials now. Why haven't we necessarily seen this same, theorized progress that we would expect in experiments or in devices that we think about when we think about sort of the promise of topological materials? And she was trying to answer that question. And one answer she gave was, if I go to one of these resulting databases of topological materials and I pull out a random system that's labeled as a topological insulator, I might find some band structure that looks like this. And this is labeled as a topological insulator when we treat these sort of blue bands here as our kind of occupied valence bands, and the red is going to be our unoccupied conduction. And so the occupied ground state here is said to have a non-trivial, say, Z2 index. Now, clearly there's a problem right away, right? If I go to the Fermi energy here and draw a line, it's not really an insulator. There's going to be electron hole pockets all over the place. It's going to be probably really hard to model theoretically, probably even worse to deal with experimentally if you're trying to get some topological signature out of this. And when we start to kind of pull at this thread more, what we realized is that most of the sort of experimentally controlled topological materials kind of come from this earlier time period here. Actually, a point that was made both by Leslie as well as in a nice perspective paper by Marcel Franz was that the largest band gap Z2TIs were identified in 2009. And so this kind of is perhaps one of the major bottlenecks to seeing this experimental progress, or progress towards the technological devices that we've been promised with topological materials. So I mentioned I learned about this in a talk by Leslie Shoup. How was she proposing to deal with this? Well, she was thinking, okay, if I have a material of interest that has maybe some topological bands of interest, like a Dirac cone near the Fermi energy, but it has all these extra bands around my Fermi energy, how do I sort of clean up this band structure, so to speak? How do I get rid of these bands that I don't want? And she was going to sort of engineer a way to do this. She was using charge density waves. This is a picture from that paper there where she's see these extra bands around the Fermi energy, and then she's going to has some method there to clean up this band structure near the Fermi energy. And of course, there are other knobs that we could tune, both in theory and experiment. We could think about strain or maybe making some heterostructure or something like that. But I'm going to suggest kind of a different way of confronting this challenge, sort of invert the process. So the idea is let's pick a few targets of interest. So for me, in my work, these targets are going to be that I want a 2D material that is stable. So by stable, I mean it has a pretty small energy above the convex hull, and then it's topological. So I'm going to be thinking about time reversal preserving spinful systems. So by topological, my target is a non-zero spin churn number. So these are my targets. And then let's borrow tools from computer science, material science, to try and sort of create some process to do inverse design. And we'll do that using one of these generative neural networks. And these things I think are really cool. The kind of general idea around their construction is that you have some neural network to be trained up here. This is your structure generator. This thing is going to generate a 2D crystal structure, and then it's going to feed it into two sort of neural networks that are already trained. And these are what we're going to call our discriminators. So these will take this crystal structure that's been produced by our generator, and it'll try to say, is this crystal structure A, topological? So in our case, does it have a spin churn number? And B, is it stable? So what's the energy above the convex hull? And the idea is that you're going to train this generator iteratively to try and basically trick these discriminators into thinking that it's created a 2D crystal structure that is stable and topological. And if you're able to do that, then you can say, maybe this is a new crystal that we just haven't worked with yet or modeled yet, and it has these features. So that's the goal. But how do we do this? Well, to do this, we need, obviously, these two necessary ingredients are these discriminators here. So the topological discriminator and the stability discriminator. And in order to make those, we're going to need a lot of training data. And we need training data that sort of fits our purpose. So in order to have this training data, we need a starting, yeah.
Sorry, so how do you assign this band structure to an imaginary material? So you generate the band structure.
No, so you're going to generate just a crystal structure. So yeah, so what's going to, you just basically atoms and the positions of the atoms in the lattice.
And then you get your band structure.
And then, right, so the way the neural networks work is their input is, which I'll show later, the input that you're giving to the discriminator, like to when you're training the discriminator, is just a crystal structure.
And you generate this material based on training data.
Yes, yes. So you need to generate the discriminators, you have to have like known training data that you can label. That's why, yeah. So we're going to have training data that we can, know, is this, first of all, a material, is it stable and is it topological? So the first thing to build this training data is we need existing 2D materials that we can classify in terms of their stability and topology. So to make this training data set, we want some existing 2D material databases. Luckily, those are in existence. There's the computational 2D material database, which is out of Denmark. And then there's another really nice database of easily exfoliable materials that is part of this materials project group. And these each have a few thousand materials. And fortunately for us, these databases also list the stability of the 2D crystals in them. So all the information that we need in order to build our first discriminator, which is going to tell us stability, is already in existence. We just have to collect this data and then train the network to predict what is, in our case, going to be the energy above the convex hull for these 2D crystals.
Is this stability based on the density function of the calculation?
Yes. So that's the first discriminator. As I said, thankfully, you don't have to do really any new calculations here. This is in existence in the current databases. The challenge is going to come in creating this topological database. And the reason for that is because there are actually already existing works where people have done some high throughput scans of 2D systems looking for non-trivial topology. But these scans are limited to what we call symmetry and indicative phases. So these are systems where you can assign, for example, a Z2 index based off of inversion eigenvalues, or perhaps you can assign a mere Chern number. And this is great, and we will definitely use this data. But the problem is that a lot of these materials that fall into this class tend to have pretty small band gaps. So things on the order of milli-eV, or maybe up to 100 or so milli-eV, 200. And our goal would really be to make something that is really attractive to experimentalists, or design something really attractive. And so for that, we want to aim for something that's going to have a band gap on the order of maybe 1 eV. And so we want to kind of increase the diversity of our training set with materials that have larger band gaps in non-trivial topology. And so to do that, we're going to have to go beyond these symmetry indicative phases and consider some of these non-symmetry indicative phases. So the reason for this is that a lot of these phases are actually predicted to appear in materials that have kind of the band gaps that we're interested in, something like 1 eV. You may be more familiar in thinking about these phases in terms of something like a higher order insulator. But I'll try to give a more concrete example of what these are and how we're going to screen for them to incorporate them into our training set. So to give a more concrete example, I want to start out with something kind of that we can think about more quantitatively. So this is the Bernovic-Hughes-Jeong model of a two-dimensional spin Hall insulator. And we can analyze the non-trivial topology of this model in a number of ways. We can look at inversion eigenvalues and assign a Z2 index. We could also get this Z2 index if you're familiar with the idea of one of your center charge spectra. We can calculate that, see that it's gapless, and that will also tell us about non-trivial topology. We could have looked at surface states here, seeing gapless surface states. All these things are in agreement. And furthermore, we can calculate a spin Chern number. So that's shown on the bottom. We have a U1 spin conservation law here. So we can calculate a spin Chern number and see that it's 1. But we have another way of probing this sort of bulk topology in this system. And that is in real space, which is kind of interesting. We can imagine taking some lattice. So on the left here is the lattice in real space. And we can imagine sort of threading a magnetic flux tube through the center of this lattice. That's that red X there. And what was shown in these nice sort of parallel PRL papers in 2008 was that if we thread this flux tube, that it will bind a number of Kramers pairs that is given by our spin Chern number. So here on the right, you're looking at the local density of states on this flux tube as a function of the flux strength. And you can see that this has a spin Chern number 1, and it's binding a single Kramers pair. And we can see that this Kramers pair actually kind of is pumped across the bulk gap as a function of the flux strength in this case. So this is a real space probe, or an alternative way of probing topology. And I'm going to show why this is kind of important or useful. So let's modify our spin Hall insulating model by including, say, these extra D-wave terms here. You can see that I've added. So this band structure still has PT symmetry, still 1 Kramers degenerate valence band, 1 Kramers degenerate conduction band. But by adding these additional terms, what we can see is that I've trivialized my Z2 index. So we could tell this by looking at inversion eigenvalues. We could also tell this by looking at my Wannier center charge spectra, see that it's gapped. And this falls under the category of what's known as a higher order insulator. It has gapped surfaces, but it has these corner modes, the corner localized modes. And we want to probe for bulk topology in this model. And what we see is that one way we can do that is by using this method of inserting a magnetic flux tube. If we do that in this model, we see kind of almost exactly what we saw before, which was that this flux tube binds a single Kramers pair. And so this is a really kind of nice, clean way of probing for bulk topology and something that's non-symmetry indicative. There is a method which we could have used in momentum space. It's actually based off of a work by Emil Proudhon in 2009, where you have to construct this auxiliary operator, which is known as your projected spin operator, which is shown on the upper right-hand side there. And then you compute a Chern number for what is sort of the negative, or the, I guess you could call it the occupied subspace of this auxiliary operator, and that will tell you that you have a bulk invariant. But this is a rather complicated model. I won't get too much into the details of it. And so we're trying to avoid doing that because you also need to know a preferred spin direction, things like this that are kind of more complicated, and we don't want to be working with that. This real space method is just very simple, direct, and something that we could potentially see using with real systems. So seeing how well this flux tube insertion worked to probe for this non-symmetry indicative topology, we went about trying to see if we can use this in realistic band structures. And to do that, our sort of proof of principle was bilayer bismuthine. We chose this because there's some nice early work, 2006, 2011, from the group of Murakami, where they looked at the occupied ground state and assigned it a non-trivial Z2 index, saying it's a spin Hall insulator, but they couldn't determine whether the spin Chern number here should be of magnitude 1 or magnitude 3. They tried to distill this by looking at edge states, but the edge states are kind of complicated here. It's hard to just draw a line through the mid gap, through the bulk gap there, and determine what your spin Chern number is based off of how many times you cut these bands on the surface. So we did a first principles calculation and then wrote this software to do this insertion in our more realistic band structure here. And we looked at the sort of 3 band gaps that you can access there as a function of filling, and looked at this local density of states on the flux tube. And what we saw was really nice and very clean and in nice agreement with what we were seeing in our tight binding models, and allows us to kind of just almost right away, without doing anything, say that the magnitude of the spin Chern number here should be 1, not 3, because we have a single Kramer's pair. And one thing I want to emphasize is that this calculation was actually pretty efficient. It was actually more efficient than if we were trying to, identify a preferred spin direction, compute this complicated projected spin operator, and do a further calculation in the bulk under periodic boundary conditions, in momentum space. So we were really excited about this results, and then it motivated us now to say, okay, we have a tool that we can use in realistic systems, and we know that it can look for this non-symmetry indicative topology. So kind of armed with that information, we decided to do this sort of high throughput real space screening. We took one of these existing 2D crystal structure databases and isolated all the systems that had been either labeled as topologically trivial or just hadn't been classified before. We basically removed all the systems that had been labeled as topological, because then there's no reason to do it again, basically. And we created this workflow to do the vortex or flux tube insertion and look for these bound modes to try to say whether these systems were topological or not. And the results were pretty exciting. There was a lot of interesting materials that we found along the way here. And most of them are contained in this archive paper here. And some kind of interesting ones in particular was this 1H phase of the transition metal dichalcogenides. That was exciting because those have band gaps that we're interested in, so right around 1 eV. But there are more materials, as I said, in that archive paper. So we did this screening, gathered up these materials, and then we also combined then our results of this screening with the results of these prior searches that had used symmetry indicators, EPRs, the typical methods to search for topology. So I would say what's different about this database is that we kind of have a more strict criteria for what's trivial. you only get, a system only gets labeled as trivial if it can't, non-trivial band topology can't be found doing this flux tube insertion. So it's a different database in terms of what we're assigning as trivial. But it has sort of some of these features we want to feed to our eventual generative model because there's a lot of materials that have larger band gaps in there. Perfect. So putting all that together, we can make now our discriminators. There was a question about how we make these discriminators, what we feed into them. We feed into them the crystal structures. So we're going to borrow an earlier method that has been seen to be really successful, which is called a crystal graph convolutional neural network. Basically, we feed into our neural network the 2D crystal, but we feed it in as a graph. So all the atoms are nodes and the bonds are edges. And at each atom, you also put some hidden vector, and that vector contains information about the atom. So valence orbitals, atomic weight, things like this. And this type of neural network has been shown to be very, very successful in material science for predicting material properties. And actually in both discriminators that we constructed, we achieved over 90% accuracy in making our predictions on a test set. So we're very excited about this. This kind of goes on its own more with this idea of discovery. So separately, we're now taking these discriminators and just trying to feed in more complicated systems into them, see if we can figure out band topology, more complicated systems.
Can I ask a question here?
Yeah.
Because I'm a little confused. So you've already got your 2D topological database where you've checked by actually calculating topological invariants and stuff. So what then is a topology predictor beyond this? Because these are already all potentially topological.
So we've created a database of materials, yes.
Right.
So these are what we're going to call our discriminators. So the way they're predicting is when we construct now the generative network. And so what's happening in this generative network, which is sort of the final product, which is the ongoing thing, is that we have a neural network which is generating 2D crystal structures.
A completely new one.
Completely
so the
new.
previous database is just for training this new network.
Exactly.
Okay, sure.
Yeah.
Missed that bit. Thank you.
So this is totally new, and it's going to generate new 2D crystal structures that are going to be fed into these two discriminators. And the weights of this generator are going to be updated, in this training process to try to basically trick these discriminators into thinking this is a real material that, it could have been something it's seen previously, a real material that has non-trivial topology. So this is what's ongoing. We've been running this, and kind of the final part here that I'll say is that now we're in the last step, which is verification. So taking the materials that have been predicted, and then actually then going and doing the density functional theory calculations to try to make sure that these are stable materials, that they are topologically non-trivial, they have the aspects we want. And then we're going to try and basically fine tune this. Can we add in other discriminators to say something about, we want to search for a particular band gap size or space for things like that. And then we have to make sure we're taking into account realistic considerations, like can we put this material on a substrate, grow it, that kind of thing. And so with that, I guess I'll finish. I don't know how much time I have, so I'll finish there.
5 minutes.
Okay, so I'll finish there.
So,
Yeah, thank you.
Yeah. And then we have a few questions from Chris apparently. Yes.
So thanks for a nice talk. I wanted to ask about stuff that doesn't make it into this kind of slimmed down description of the crystal structure. So I spent some time thinking about oxides. People talk there a lot about octahedral rotations, tilts, how this pushes the thing sort of sequence of glitches, transitions. You might have thought that if you were thinking of opening bulk gaps, that would be important, but it sounds like none of that stuff actually survives in your descriptions.
Yeah, that's an interesting thing. There are various, this is where it's hard because it's kind of not a perfect, we don't really understand all the time what makes a neural network work better than others. There are kind of standardized data sets that people feed into these. I don't know if you're familiar with this MagPi way of doing things. That's one. Yeah, I mean, sometimes you feed more information, you get worse results, kind of. I think in this case, when it comes to the topology aspect, you know, we're definitely including things like what are the valence orbitals, things like that. But those are interesting ideas. I haven't thought about much. And when it comes to band gap, feeding that kind of information would probably be important.
I mean, maybe what it says, stop obsessing so much about the stuff that the because it's not statistically representative.
That could be too. Yeah, it's hard to say.
Alina was next.
So when you're describing what we put in the neural network, it's essentially everything. I don't know, maybe I naively with the atoms, the crystal structure, from the distance between the atoms, the balance. So what is there that we're not including? First question. And the second question is, do you learn any guidelines from doing this exercise? If I don't want to just put things in my computer, but I want to try to understand why are these realizations the most interesting, bigger gaps? Is there anything you learn out of these exercises?
Yeah, it's an interesting question. I think a lot of these things we probably already knew in terms of what we put in. I think, you know, one of the things that seems to be very helpful is like space groups. Some space groups just seem to, for some reason or another, support this kind of, and I guess there are symmetry considerations there that we are considering, but, you know, putting in space groups, for example, putting in valence orbitals. So what combination of valence orbitals and the occupation of those valence orbitals is sort of most important.
Site symmetries, how information is there somehow, but is it an explicit variable?
The site symmetry is not. There have been actually previous studies where people have used these crystal graph to try and predict things like that. So I think it seems that these crystal graph networks have the ability to interpret that kind of information on their own, just from this basic information. But yeah, in terms of what we're leaving out, I mean, we are leaving out a lot of things in terms of like, there are other neural networks that take into account things like the eigenvalues in particular, like what is the density of states, things like that. And that's information that would involve more calculations.
The
And
more raw information, what would be the most raw piece of information that gets the
most raw piece of information that would give you insight, I think, has to do with valence orbitals.
It was one question.
Thank you for this nice talk. Very interesting. So I have a question regarding the metaphor of magnetic flux.
Uh-huh.
So this is how we determine if the material is topology.
How we search for band topology, yeah.
So does this method work for every material? Like whether it's magnetic or not? Also, I think there is other probably methods to determine whether it's topology or not. But for instance, it's a finite version of the whether it's
Yes. So the first question, does it work for everything? It works for, at least it works for spin Chern numbers. And, you know, if you have something that has a Chern number, just an anomalous Hall insulator, it will identify your Chern number as well. It doesn't work for all invariants, but at least for what we're thinking about with a spin Chern number, that in that case it does work. And like you said about edge states, corner states, there are separate works that have done sort of screening for corner states or edge states, like you're saying. One thing I'll say is that I think it can be harder, at least from my perspective, to interpret those results. These seem to be pretty clean. Corner states, you know, in a lot of cases, they don't have to be pinned at zero energy or in the bulk gap or that kind of thing. Those kinds of things can vary and fall within our you know, bulk states. So it can be harder to identify those, but there are studies that have tried to do that. Yeah.
Last question.
In terms of real samples which can be measured and the topological effects detected, I mean, in reality, there are lots of bands besides the topological bands which often are found. And that will dominate the transport behavior, for example, to make any of this material useful in applications. So I wonder which will be the best candidate. I mean, how can you add another layer to say, okay, we find topological features, but it's 20, 1 electron volt below the Fermi level. How do you identify those materials which are really useful for applications?
Yeah, I think that it's maybe a little bit built in for us because we're not going to be considering individual bands here. I know that that's sort of what they did in most recent high throughput searches. We're looking at ground state topology, and just even our method itself is looking at what are the states within this bulk gap. So we're going to be sensing it when it's inside the bulk gap and having a nice clean bulk gap. We're not thinking about something that's a semi-metal or something like that. It has to be a genuine insulator for us to use this method. Yeah.
Last question, Piers.
This will work for weakly interacting systems. Most time, I know of a number of apparently topological insulators which are not supposed to be topological insulators according to density functional theory. Samarium hexaploid was the first example, but there's now iron silicide, iron diantimonide. These systems mysteriously seem to be topological insulators, but band structure in its current form doesn't predict it. Any thoughts on what might be ahead, what we might try to do with neural networks or machine learning? Could you feed it these examples if you had enough of them and teach it to sift them out?
I mean, there may be, so I would have two quick answers. I'll try to get through those. The first is that I like this idea of thinking about correlation and topology because I also think this magnetic flux is a real space probe. So it could be a really nice way to think about probing topology and correlated systems because you can think about things that maybe break your translational symmetry and still use this as a probe. So I'll say that first. But the other thing that I'll say is that, if you wanted to do that, maybe you could start to incorporate into your networks, like what kind of Hubbard U do you need to accurately model this in DFT or something like that? What are other considerations that need to be made to have accurate DFT?
Yeah, I see. Yeah, you could imagine DFT with you in it, some broken symmetries or localized moments. Yeah.
Exactly, thinking about things like that.
Good.
Okay, with that, we better move on. So let's thank Alex again.